All right, we're going to spend a few minutes and talk about color and where color comes from in astronomical pictures. Now, if you think back to grade school, in art class, you probably learned about the primary colors of paint, and those were red, blue, and yellow. And maybe more recently, you may have heard about cyan, magenta, and yellow, right? These are specifically, being a little more specific than just red, blue, and yellow, these particular shades of red and blue are truly the primary colors of paint or pigment or ink in a cartridge. Cyan, this bluish color, magenta, and yellow. And when these colors are combined with one another, like when you mix the paints together or the pigments together, you can make lots of other colors, right? So you may remember that mixing blue and yellow makes green. Well, really mixing cyan and yellow makes green. And we can see how green that really is. That's really kind of pure green. Mixing cyan and magenta makes blue, and mixing magenta and yellow makes red. Okay, so you're probably familiar with this idea that mixing colors can make new colors. What's weird is that we've only really done this with paints and pigments, right? In astronomy, we're dealing with light. And when you're mixing colors of light, the rules are slightly different. So take a look here. There are, again, three primary colors, but when it comes to light, the three primary colors are red, blue, and green. And not shades of those, but like the purest you can imagine, red, blue, and green. And similar, you can almost imagine that these are sort of squares of light that I'm shining like through a flashlight, right? And if I were to have some of that light overlap, new colors can be made. So for example, if I overlap red and green, I get yellow light. All right, and if I overlap blue and green, I get cyan. And so maybe you can guess if I overlap red and blue, I get magenta. And what's interesting here, of course, is these are related to each other, right? The primary colors of paint and the primary colors of light are connected. What's also interesting is when I overlap all of these things together, right? All three of these colors when it comes to light, what color do I get in the very center? I get white light, right? So white is light that has all the colors in the rainbow. Now you probably remember that when you think back to paints and pigments, if you mix all the colors in the pot together, you end up with a really dark brown kind of black paint, right? So it points to the fact that these two things, mixing light and mixing paint, are doing fundamentally different things. When we're mixing light, we're adding the different colors of light together. When we're mixing paint, we're subtracting colors from one another. So we're looking at light addition here and color addition when we're looking at light. Now this tells us something about how we get colors in all the different things we use, really, in particular with screen technologies, right? So we're looking at screens almost all day long, it seems, between televisions and computers and cell phones, and the colors on those screens is coming from this idea of color addition and of light being combined. If you've ever looked up close at a television screen or a computer screen, this is actually what you see, right? Is that there's these glowing phosphors in the old-fashioned TVs, although now it's sort of like pixels in your sort of modern televisions. And these pixels are glowing in red, green, and blue. And the amount of red, green, and blue is what's telling us what these different colors are on the screen. It's quite an amazing thing. It's almost like pointillism, right? The style of art where all these tiny little dots make up a complete picture. So really it's about the ratio of these three primary colors that tells us what the color of any given pixel is. Let's look at that in a different way. Here's a little simulation with this guy, and he's looking at some light, and what we're going to do is we're going to combine different colors of light. So here I have a red light. I'm going to turn it on, and you're going to see the photons flying at him, and we can see what he's thinking. He's thinking, oh, this is kind of a reddish light, and it's a little dull, right? And maybe it's bright red if I turn up more photons. Right, so now it's a little kind of a brighter red. Now, if I were to turn on some green, now you can think of these as the glowing pixels in a television or a computer monitor. Right, I turn up some of the green. Now he's not perceiving the red and green separately, but they're combining together. And as we saw before, when red and green combine, we get kind of a yellowish color. But now, what if this green was turned down a little bit? Right? If I only have maybe half the amount of green as red, then when that signal kind of gets to this person, you'll see that the color turns more kind of like an orange. Right? So we saw several colors when we combined the colors before, right? Like you could see that we could make yellow or we could make cyan magenta, but all those colors in between can be made up by varying the ratios of these different primary colors. So let me turn down the screen even more, and let me turn up some of this blue. Right? So by varying the amount of red, green, and blue, I can make truly any color imaginable. You can see now I'm getting kind of like a hot pink color. All right, that's pretty slick. Now, in fact, this is true already of the images that we look at every day. Let me just pull up a picture that we've seen. Let me stop that so it doesn't slow us down here. Here's a familiar picture, right? This is the Pillars of Creation, the Eagle Nebula. What I'm going to do is I just want to show you that in this picture, all of these colors are actually made up of just certain amounts of red, green, and blue. Now, I opened a different window here on the right-hand side, and what I want you to notice is that the second line down there says RGB, and there's three numbers. Right now it says 216, 225, and 239. That is the amount of red, green, and blue light that's being shined in this particular pixel that I'm pointing at. So I can point at any particular pixel that I want to. So let me point at sort of this like blue-green background. And you'll see in that little square in the upper right that it's sort of isolating what the color of this one pixel is. And if I want to make that color, I need 47 units of red, 83 parts of green, and 79 parts blue. It's almost like a recipe for making a particular color. If instead I want to make this kind of pink color here, right, that's the ratios. Of course, there's more red, right, 215 red, 116 green, and 171 blue. Previously, we saw that a digital image is really just a table of numbers. It's an X and a Y location and a single number telling you the brightness in that location. What we're seeing now is that this table is a little more complicated. In a color picture, it's an X and Y pixel location, but at that one pixel what we actually have are three numbers. A number representing the amount of red, the amount of green, and the amount of blue. And those three numbers together uniquely can tell us the color of that pixel. Right? But it's still just a table of numbers. We've just added sort of additional color information now to that table. You'll notice as we look at this particular image, which this is a JPEG file format, you'll notice that all the RGB values are less than 256. In fact, if I go at a pure white right here in the middle, or pretty close to pure white, you'll see that I have 255, 248, 255. In fact, this is a sort of standard 8-bit image. It only has from 0 to 256 levels of red, green, or blue. As we saw before, a FITS image, this .fits, has 60,000 levels to it, right? It's like a 16-bit image. And so there's way more, not only brightness information like dynamic range, but potentially way more color information. Right? So if you want to be able to make millions of colors, then you want to have lots of different levels of red, green, or blue that you can combine to make subtle variations in color. Now, when we looked at an example of an astronomical image before we looked at a galaxy, it was a black and white picture. And in fact, all astronomical pictures that are taken by professionals are black and white pictures. And so this issue we're going to face is how do you get a color picture from a black and white picture? Now I want to point out to you why we take black and white pictures when we're taking astronomical photos. Look back at this image of a screen up close, and this is very similar to what a color digital camera would have to look like. If you had a color camera like in our cell phones or the digital cameras we carry around, it takes color photos. The problem is you need a pixel that's sensitive to red, a pixel that's sensitive to green, and a pixel that's sensitive to blue light, and all of those have to come in to a single pixel. So if you think about it, if you look up close at this, right, one pixel here is actually composed of 3 pixels, sort of, right? It's just we have to use one for each of the 3 colors. Now, in astronomy, we want the highest resolution possible. We want to be able to see the smallest possible details. And in this case, we're sort of wasting 2/3 of our pixels, right, just to get color information. Because in the width of one big pixel here, I actually could fit 3 smaller pixels. So in astronomical photos, what we do instead is we capture black and white images, and then we combine them on a computer and put the color information together in the computer, rather than doing it all in a single picture. Now what that means is we have to take 3 separate pictures, a red picture, a green picture, and a blue picture. But in doing so, we're keeping a very high resolution. So it takes more time, but we have lots of time. What we really strive for is the highest resolution possible. And this leads us to the final topic I want to chat with you about in this video, which is filters. To talk about filters, we're going to return to this simulation and we're going to look at it in a different way. This single bulb. So this is a case where now I have a white flashlight. And that white flashlight, you can see, is sending out photons of all different colors. But by having a filter in the way almost like a piece of plastic that's a certain color, it blocks out all the colors of light except the color that I want to let through. So what astronomers do is they will take 3 pictures. They'll have a filter that is, for example, a red filter, so it's only letting through the red light, and they capture a black and white image of that red light. And then they switch filters and they'll use a green filter, and they'll take a black and white image of the green light, and they'll switch filters again and they'll do a blue filter, and they'll take a black and white image of the blue light. And so you'll end up with is 3 black and white images. And if you think about it, each one's a table, right? And each one represents the amount of that specific color. And so we can combine that data together, those numbers together, and make a single image, which becomes a color image because every pixel contains the amount of red, green, and blue light. You can see that illustrated here from the Hubble site. They've kind of tried to explain this. And what's beautiful about this is that cameras can even detect light that our eyes can't see. So we can take pictures not only with red, green, and blue light, but we can take pictures with infrared light or ultraviolet light. And we can see what those look like, and we can even combine those and make color pictures that extend beyond what our eyes could ever even see. And we'll get a chance to do this ourselves. But let me just show you, here's a galaxy. We can see what it would quote-unquote really look like, the light passing through. And if it passes through an ultraviolet filter, you see here's a black and white picture of just the ultraviolet light. Here's a black and white picture of just the green light. Right? And here's a black and white picture of just the red light. And we can also see the infrared. Now these could be combined on a computer, right? And we could turn it into this color picture. So let's take a look at what that might look like. On the left here, you can see I have a red, green, and a blue. And on the right hand side, I can add them together on the computer screen. So if I take my black and white picture of red light and I assign it all the color red, right? Then I've got the red light here, and I can add on top of that the green light, right? And now it looks kind of yellow. I can add on top of that the blue light, and in principle, I'm reconstructing what this thing really looks like. But as you've already seen, you can adjust the amount of red, green, and blue to kind of get different shades a little bit, right? So there's some freedom here in terms of when we're making a real color picture of an astronomical object to try to figure out exactly what that object really looks like. Later in this lesson, we're all going to make our own color astronomical picture using the principles that we've seen here in this video.